Hey, welcome back. I hope everybody has a great spring break. On the board is actually the things that I summarized for you. These are all the contents that we're going to learn for chapter 15. Okay, so the goal of today is to finish this chapter. Okay, and hi. Okay, so we're going to finish this today. Okay, that means actually you're going to have all the things you need for your midterm 2. And we still have 2 more questions for this chapter hangout. We'll finish that. And after that, we're going to go to a review hangout and finish all the questions related to chapter 15. On Thursday, we're going to revisit chapter 13 and 14. Okay, so I will also write something like this, so you know what are the things that you really need to memorize. Okay, and we do all this simply because I want you to have everything ready. Okay, so the exam section next week. Okay, so I really hope that we can still keep our grade tradition that our midterm 2 grade doesn't really drop too much. Okay, so let's go through this thing quickly. For chapter 15, it's all about the solubility. Okay, solubility of an insoluble salt. Okay, so here I use AX plus AX BY to represent my insoluble salt. Okay, and the A represent the cation part, B represent the anion part. Okay, you need XA, YB to form one insoluble salt. Okay, one thing that we need to become a master is that every time we see an insoluble salt, okay, we know how to write down its dissociation equation. The reason that is important is because this will be actually the final form to calculate your solubility constant KSP. Okay, of course, you calculate QSP in the same way, but only when the system at equilibrium, then you know you have a constant KSP, right? So we sort of practice this one before the spring break, and we'll probably actually go through a few examples today as well to refresh your memory. But let's actually the number one things that we learn when we start this chapter. Okay, so that's actually something you need to actually become really good at it. Okay. After that, okay, no, not after that. Okay, so one thing that's so important in this type of questions that in the questions very often you are going to given the so-called grain solubility. But you cannot just use the grain solubility to calculate your KSP. You need to use the molar solubility, which has a unit of molarity. Okay, so if you see gram per milliliters, you need to convert it into moles per liter to do your KSP calculations. Okay, otherwise you will never get the correct number. Okay, so let's actually first big topic for chapter 15. Then the next question is actually the question asks you, okay, if I mix 2 solutions, 2 soluble salt together, okay, and each solution contains one of the ions for your insoluble salt, right? Can you compute the QSP yourself? Okay, so the calculation is actually exactly the same as the KSP. Okay, so when you compute the QSP, then you compare that to your KSP. One key knowledge that we must have is that if your QSP is larger than your KSP, okay, that means actually you have too high concentration of your anion cations. Okay, they're going to form the precipitates. Okay, if the QSP is larger than your KSP, then precipitate will form. Otherwise, it won't. Okay, so the comparison between your QSP and KSP is another big point for this chapter. Okay, so those are the 2 things that we went through before the spring break. Okay, so what we are going to do and finish this chapter is actually by introducing you another two important concepts. Okay, so the first concept we're going to talk about is that if today you have a insoluble salt dissolving inside aqueous solution, if I add in acid, which H plus, or if I add in OH minus, how will it change the solubility of that insoluble salt? Okay, should it be increase or decrease? Okay, so that's actually the main thing that we're going to actually learn. Okay, so the basic principle to make the proper judgment is that you need to check the anions of your insoluble salt. Okay, so the reason you check anion is that if you check that these things has to be sensitive to H plus or OH minus, right? That means actually the species need to be either strong acid or strong base. Okay, so H plus doesn't actually form insoluble salt often. Okay, the things that can form the insoluble salt typically is actually OH minus. Okay, or some weak base. Okay, therefore you want to actually look at the anion part to actually predict. Okay, so the idea is actually very simple. They say if your anion is OH minus, okay, that means they say you have this. The A just represent any cations, okay, but if complex with hydroxide to form an insoluble salt, okay, and once it dissociates, it's going to be have. I guess I can give you a real number. Let's say this. Aluminum hydroxide, okay? Then it will be Al3 plus 3OH minus. Okay, so this type of equation, you actually learn how to write it yourself. Okay, so let's say we have this insoluble salt, aluminum hydroxide. Once it dissociates inside your aqueous solution, you're going to form Al3 plus and 3OH minus, right? So if today you add in H plus into your solution, what's going to happen? Because H plus is a strong acid, right? It's going to kill all the base. That means this guy will interact with H plus, right? Therefore, the amount of your OH minus inside solution will decrease. Okay, but we know the KSP is a constant. That means actually you must have a finite concentration of your OH minus exist, right? But right now, all your OH minus was killed by your H plus. Therefore, the insoluble solution actually dissolve even more to compensate for the change. Okay, everybody follow the things I say? Okay, so if you add in H plus to this aluminum hydroxide, the solubility of that insoluble salt, which is AlOH3, is going to increase. Okay, so this is actually why in this table, I say if I add in H plus, the solubility is going to increase. Okay? On the other hand, if today you did not actually add in H plus, you add in OH minus. Okay, so now you have overwhelming OH minus inside your solution, right? So those overwhelming OH minus will actually further react with your Al3 plus to bring it back to the AlOH3 form. Therefore, the solubility will decrease. Okay, and that's actually why I put decrease right here. Okay, so that's actually a basic idea. Everybody follow this? It is very important to understand why it actually increases and why it decreases. Because once you understand the concept, then when you actually apply these things to different questions, it will be actually quite simple. Okay. The other situation you may encounter is that if you have a weak base, okay, so instead of have OH minus, you actually have a weak base. Okay, So once you dissociate, you produce a bunch of weak base. Okay. And the same scenario apply. If today you add in more acid, that acid will interact with your weak base. Okay, so your weak base will be diminished. Under the case, to maintain the same K, your insoluble salt needs to actually dissociate more. Therefore, the solubility is going to increase. Okay? The only difference between your weak base versus hydroxide is that if you have weak base and you add a strong base OH minus, they won't interact because they are base and base, they don't actually kill each other, right? So under the case, there's actually no effects. That's why I put a cross for the weak base overlay. Okay? So those are the key things that you need to actually really memorize. Okay. So another situation is that if the anion is neutral, okay, if your anion is neutral, what condition you're going to have neutral anion? This actually go back to chapter 13. Okay, what anion will be neutral? It will be the conjugate base of your strong acid. Okay, so iodide, I minus, bromide, chloride, chloride. Okay, those things, SO4 2 minus, NO3 minus, those things they're actually neutral. Like in acid and base doesn't actually influence or doesn't change the solubility. Okay, so those are the basic things that we need to actually memorize and understand. Okay, so using the concept, then we'll be able to actually solve these questions. Okay, so this is actually one of the questions you're going to see quite often in the quiz, and I think probably actually you'll see something like this in the midterm as well. Okay, so the question says, which of the following compounds will have different solubility with lower pH? Okay, what are the keywords here? Yes, solubility. And then there's actually another keyword here. Lower pH. Okay, what does lower pH mean? Lower pH is actually more acidic, right? Meaning you're adding in H+. Okay, so when you add in, this means you add H+ into your solutions. Okay, so you need to actually have that understanding. Okay, if today I say how this solubility will change with higher pH, then you know you're adding OH minus. Okay, so you need to actually read the text and know what's actually really changing. Okay, so this actually meaning you're adding H+. Okay, so this actually really just for the things we talk about, right? So if you see these things, right? AgNO3, I said you need to actually use the anion to make your prediction, right? So here you need to actually learn how to write the cation and then the anion. Okay, so you need to actually know the things that dissolve inside your solution is Ag plus and NO3 minus. Okay, then you want to actually know the anion, is it a strong base, weak base, or neutral? Okay, so NO3 minus, is that strong base, weak base, or neutral? Neutral or weak base? When we say strong base, everybody know I mean OH minus, right? Apparently it is not OH minus. Therefore, it cannot be a strong base, right? So now you're actually debating between neutral or weak base, right? How do you know? The easy way is actually to write out is conjugated partner, right? its conjugated partner will be HNO3, right? When I say conjugated partner, it's actually either you plus one H plus or you subtract one H plus. NO3 doesn't have any proton you can actually further subtract, let you know you have to actually add the H plus to find the conjugated partner, right? So HNO3 is a strong acid, right? Everybody still remember the big sevens. Okay, HNO3 is actually one of them, right? Therefore, you know that's a strong acid, therefore its conjugated base will be neutral, right? Since the anion is neutral, that means it is not sensitive to all this H plus or OH minus change. It's not going to be sensitive to the pH value. Therefore, the solubility will not change. Okay, so this is actually how you know it's going to increase or decrease. Okay, so for this one, then we know no change. Okay, how about this guy? What's the ions of CaCl2 once it dissociates? Ca2 plus. And then 2Cl minus, right? How many of you actually know exactly how you actually write these things out? How many of you, it's not very clear? Be honest with yourself. There's only 1 week left. You better actually know how to do it. How many of you still don't know how to write the things? Everybody know? Be honest with yourself. Let me ask one last time. Okay, if I need to actually go through that, I will go through that. How many of you still don't know how to write these things? Okay. Everybody have your periodic table? All right, so I really want you to actually have your periodic table with you. Okay? It's very useful but inconvenient. If you don't use it, you're actually missing the opportunity to actually get the easy points. If you see a compound contain any elements in that first 1A column, okay, once they dissociate, they produce positive 1 Ki ions, meaning that lithium, sodium, potassium, those things will become lithium plus, sodium plus, so on and so forth. Okay? Second column will be positive 2. Do you see that calcium is actually one plane? We just go through this calcium chloride, right? How do I know it's calcium 2 plus? Because it's a 2A element. Okay. The periodic table was actually arranged in a very specific and logical way. Okay, so you need to use that to help you study. Okay. How about the things in the 7A? The fluoride, chloride, bromide, iodide, that column. That column, once they dissociate, it always carries -1. Okay, calcium chloride, CaCl2, dissociate become cation will be Ca2 plus, Cl1 minus. Okay, if you have this concept, writing out those things is very simple. Okay, so if you haven't actually really used this one, use it. Okay. All right, get back to this. I hope right now everybody can see why I write Ca2 plus and 2Cl minus. Okay. Then we look at the anion. What's the anion that we have? Cl minus, right? Is it weak base or neutral? Neutral, right? Because it's actually the conjugated base of HCl, which is a strong acid, right? Therefore, it's neutral. Therefore, pH has no effect on the solubility. Okay, so this guy, neutral. Therefore, no change. Okay, how about this? What are we going to write? CaOH parenthesis 2. Okay, you know the Ca will become Ca2 plus. I hope by now everybody know why I write Ca2 plus. Okay. And then 2 OH minus, right? I assume everybody know OH minus is actually 1 minus, not 2 minus, right? So 1 minus. Okay. So what's OH minus? A strong base, right? Should be actually very straightforward, strong base. If you add in H plus, it's going to consume your strong base, right? Okay, to compensate decrease, that means actually your salt need to dissociate more. Therefore, the solubility of your insoluble salt will be increasing, right? So that's how you know the answer is increasing. Okay, if you add in more H plus, the solubility of your CaOH2 is going to increase. We good? Next one, CuCl. Okay, when we write out CuCl, okay, do you know the charge of your Cu? Because Cu doesn't belong to your 1A, doesn't belong to your 2A, right? But does it matter? No, it doesn't, because all you care is actually the anions. What's the anion? Cl minus. Okay, Cl minus is the conjugated base of a strong acid HCl. Therefore, it's neutral. Therefore, no change. Okay, very simple, right? If you can see these things, then things become very, very easy. But if you don't, you feel very confusing. Okay, next one. BaCrO4. Okay. If you check your periodic table, does Ba belong to 1A or 2A? 2A, right? Therefore, you know once they dissociate, you're going to have a Ba2 plus, right? All the remaining things, which will be CrO4, 2 minus, right? So now you need to ask yourself, CrO4, 2 minus, is a strong base or weak base or neutral? Weak base. Apparently, it's not strong base, right? Because it's not OH minus. Okay. And then if you look at like conjugated acid of that guy will be H2CrO4, which is not a strong acid, right? Therefore, it's actually a conjugated base of a weak acid. Itself is a weak base. Okay. So if you add in H plus to that weak base, it's going to kill that weak base, right? Acid and base, they're going to kill each other regardless they are strong or weak. Since you are going to kill that means actually the salt needs to actually further dissociate to produce that to maintain the constant. Therefore, under this case, the solubility will increase as well. Okay, so this is actually a fundamental logical thinking to solve a question like this. Okay, you'll go back down to can you actually recognize the anion that you have is neutral, strong base, or weak base? Okay, so this is actually the question that I want to go through for you. Any question for this? Let me actually take the snapshot of this. Strong base, weak base, add in acid, add in base. That's all the possible things that you're going to have. Okay, so if your anion is actually neutral, nothing's going to happen. Okay, but depending on your actual strong base or weak base, adding acid and base is going to change your solubility slightly differently. Okay, then you need to actually really recognize the way it changed. Okay, so remember, every time I summarize things for you, okay, those are things that you need to memorize. Okay, so having this is going to be very helpful when you do your questions. Okay, but unfortunately, you need to actually memorize these things. Okay. All right. Any other questions? We good? Then we go to the very last topic for chapter 15. Compound ion effects. Okay. So this is actually very last topic that you want to actually become a master. Okay. So by now you should actually know how to write the dissociation equation of an insoluble salt, right? And then you should actually know how to compute your KSP. So this type of question is that I'm going to tell you I have an insoluble salt. Okay, and then I tell you the KSP of the insoluble salt. And then I add in some soluble salts, which the soluble salt contained either the same cation or the same anion of your insoluble salt. And I ask you what will be the solubility of the insoluble salt after I add in the common ions. Okay, so that is a type of questions, the very one last type of question you're going to encounter for this chapter. Okay, so how do you actually handle this? I think it's easiest to just do a questions, then you understand what it means. All right, so let's read these things together and carefully. It says the KSP of AlOH3 is 1.0 times 10 to the negative 33. What is the solubility of that guy in a solution contain AlNO3? Okay, give your answer using the scientific notation and blah, blah, blah. What are the keywords? Yes, solubility, wonderful. Okay, so which one is your insoluble salt? How many species you have in this question? 2, right? One is AlOH3. The other one is AlNO33, right? Which one is your insoluble salt? Which one? The one with KSP information is your insoluble salt. Okay, KSP is specific design for the insoluble salt. Do you guys see that? Okay, because if it's soluble, then it pretty much can dissociate 100%. There's no meaning to define the equilibrium concentrations. Right? Because it's insoluble, therefore the amount is limited. Okay, once you reach equilibrium. Okay, therefore, whichever compounds that has the KSP, you know it is a insoluble salt. Is that clear? Okay, very easy to recognize, right? Now let me ask you again, which one is my insoluble salt? AlOH3, very well. Okay, then what's the other guy? What's the other guy? It's a soluble salt, right? Because you don't have KSP, therefore you can think, okay, there has to be a soluble salt. Okay, what do we mean by soluble salt? It's going to dissociate 100%, right? Now tell me, if you look at that soluble salt, AlNO33, right? Once it dissociates, what's the cation it produces? Al3 plus, okay? And anion will be NO3 minus. Okay, you have 3 NO3 minus, right? Okay, so why does that important? It's because this is actually the dissociation equation for your insoluble salt. I assume everybody can actually write this themselves yourself now, right? And then when we talk about the solubility, okay, the solubility is actually solubility of this guy, right? And then once you have the things dissolved, that's the eventual concentration you're going to have for your aluminum 3 plus and OH minus, right? For the aluminum 3 plus, the solubility concentration is actually S. Then the concentration for your OH minus will be 3S. Everybody know why I write 3S over there? Because the coefficient between your insoluble salt, which is 1 here, to this means actually 1 insoluble salt. Once it dissociates, it produces 3 equivalent of OH minus. If you know the concentration of the solubility of your salt is S, then since you produce 3 times of that, therefore the amount, the concentration will be 3S for the OH minus. Okay, everybody follow that? Okay, something that you must actually know why. Okay, something you must actually be able to write yourself. Okay, so let's actually, the solubility, the concentration of your Al3 plus and OH minus you're going to have if you only have your insoluble salts. Okay, however, you are not actually just in the solution only contains your insoluble salts, right? What else do you have? You have your AlNO33, right? That guy's going to dissociate 100%. That means it's going to produce what? Al3 plus as well, right? A common ions that your insoluble salt also have, right? And since right now all of things is actually within the same container, therefore the concentration of this guy will be the solubility of your insoluble salt plus the contribution from that guy, right? Also concentration of your AlNO33, 0.01, right? That means actually for your Al3 plus, the concentration will be that much instead of just a S. Okay, everybody understand what I'm doing now? Okay, can you actually do this yourself? You need to, okay? Whatever I'm doing right now, you need to do it yourself. Okay, so once you understand this, the next thing is actually, okay, then ASP is basically the same. It's going to define us this concentration first power, that concentration to the cube, right? That's the definition of equilibrium constant. Okay. Then the concentration of your Al3 plus will be S plus 0.01. The concentration of your OH minus will be 3 times of your solubility to the cube. Yes. Okay, so why? Where the 0.01 comes from? Comes from this guy, right? So what would you write once your AlNO33 dissociate? Can you write Al3 plus 3NO3 minus? I assume everybody can do this. Okay. And then you have AlNO3 have this concentration to start with, right? And you know all of them will dissociate. But because the coefficient ratio of them is actually 1:1 for your aluminum, right? Therefore, this guy will be fully consumed because you dissociate 100%. Then you produce less much of Al3 plus. You're going to produce less much NO3 minus, right? These are the species they are going to have inside your solution. You have aluminum, you have NO3 minus, you have OH minus, right? But when you're trying to write out the equilibrium constant, all the things that you care about are your Al3 plus and then OH minus. When you throw in your AlNO3, this is actually a species that's actually the same with the species you want to use for your calculation, right? It doesn't produce extra OH minus. Therefore, I didn't actually write anything else here, right? I just keep 3s. Okay? And that's why I write things like this. Okay, because all the OH minus is solely coming from your insoluble salt, right? The species you add in, the soluble salt you add in, doesn't contain slag. But if today you store in a soluble salt, for example, you store in NaOH, okay, then it will be the second term that you add in whatever concentration generated from your NaOH. Does that make sense? Okay, if it doesn't, then we should connect after this. Okay, but why do we call this common ions? It's because the soluble salt you add in this case, AlNO3, the common ion you have in between the soluble salt and insoluble salt, in this case, is your aluminum 3 plus. Okay, so they need to actually be considered together. That's why I need to write S plus 0.01. Okay, and then for the OH minus, your insoluble salt is actually the only substance that can produce OH minus. Okay, therefore I still keep 3s only. Okay. So once you can understand this, then we come to these points, right? You have this. It's going to equals to your KSP 1 times 10 to the negative 33. Okay. So in this type of calculation, okay, in chapter 15, one thing that you need to actually know is that the small x approximation always holds. Okay. That means actually the solubility level we have here compared to these values, you will be very, very, very small. Therefore, you can always approximate that this equation into 0.01 times 3s cubed equals to 1 times 10 to the negative 33. Okay, therefore 3s cubed is going to equals to 1 times 10 to the negative 31. Okay, then it will be your time to use your calculator, right? So if you take the cubic root of that and divide it by 3, then you can get the things that you're going to get is 1.55 times 10 to the negative 11. Okay, and that will be the answer you're going to input. Okay, so let's pretty much how to solve the common ion effects. Okay, calculation. Okay, so recap quickly. Okay, for this type of questions, okay, it's going to tell you insoluble salt formula with a specific KSP. Okay, and it will ask you what is actually the final solubility of the insoluble salt if I add in the second substance. Okay. And that second substance will contain common ions, either the same K-ion or the same anions, right? So the things you need to do is actually, when you write out like KSP equation, Okay, one of the things you need to actually add in the concentration produced by your soluble salt. And then you use the small x approximation. Okay, and then you solve your solubility, and that will be the answer you're looking for. Is that clear? Okay, so this is actually a type of question you're going to see over and over again. Yeah, so it's extremely important that you can recognize who is the insoluble salt, who is actually a soluble salt, and what is actually your common ions. Okay, if you can see those things clearly, this is actually a very simple calculation. Okay, one thing I want to mention is that, what's the answer here? 1.55 times 10 to the negative 11, right? How many of you actually display your answers in scientific notation on your calculator? Okay, now everybody, right? If you don't do that, what are you going to see? 0. Will I count as correct? No, you lost all the points. Or, okay, you get nothing. So know how to actually make your calculator display scientific notation. It's extremely important for chapter 15 because the number you get is always going to be extremely small. If you don't do that, you'll realize all the answer you got is always 0. Okay, so pay attention to that. Cool? All right, so let's actually all the questions for the Hangouts. Okay, chapter 15 Hangouts. Okay, now I want to actually go to the review. Okay, and you're going to see the same questions over and over again. So in the Hangouts, okay, so the very last 6 questions in the review Hangout, if you download today, okay, from the link, okay, the very last 6 questions belongs to chapter 15. Okay, so we're going to go through those questions as much as I can. Okay, first thing first. It says at 25 degrees C, the solubility. Okay, I hope that you see that that's the keyword, right? Solubility, chapter 15. Okay, of barium carbonate is 9.0 times 10 to the negative 5 mole per liter. Calculate the value of KSP. Okay, this guy, I think right now they give you the chemical formula. Okay, so it will be this. Okay, BaCO3. Okay, they want you to calculate KSP of this, right? So the Q is actually to calculate your KSP. Data that you have is, you know, you have BaCO3 insoluble salt. Once they dissociate, it becomes Ba2 plus CO3 2 minus. Okay, and the KSP should equals to Ba2 plus concentration times CO3 2 minus concentration, right? So all you need to do is actually figure out the concentration of lead, then do the calculation, then you'll be able to get the answer. Okay. What's the concentration of your Ba2 plus? Nine times 10 to the negative 5 moles per liter, right? How about your CO3 minus? What's the concentration of CO3 minus? Yes, it is the same value. So what's the answer? Is this correct? Yes, it is correct. Why you guys are hesitating to say it is correct? Why? Yes, you're scared, right? Why? Because you are not sure, right? So what other things they need to check? Solubility, right? Therefore, to calculate your KSP, you must use molar solubility, okay? Which is a unit of M, right? Molarity, right? Which is mole per liter, right? So do you have late unit? You do, right? Moles per liter. You know you have correct unit, okay? Then the next thing you need to be careful is that the compounds, once they dissociate, okay, the concentration has the 1-to-1 ratio, right? If it doesn't, then the number needs to actually multiply like coefficient. But in this case, do you have 1-to-1 ratio? Both for your Ki and Ni has 1-to-1 ratio to your insoluble salt, right? Therefore, you just write down 9 times 25 for your Ki, 9 times 25 for your Ni. Okay, and then you multiply, and that's it. That's the correct answer. Okay, why do I actually put a simple question like this here? It's because you always question yourself, right? It's the simplest question you can actually have. Okay, but many students is not sure, right? And then you think and think and think. Then this easy question takes you 5 minutes. They later on realize, oh my God, I run out of my time. Okay, so come back to the simple things that I say, right? Do you have the correct unit? Yes. Okay. The ratio is actually 1-to-1. Yes. Then just do it. That's it. Okay. If today, let's just do something else. Let's say I have 9, the same concentration, right? 9 times 10 to the 5, and CaCl2, calculate KSP of that guy. Okay. First, again, check the unit. You have correct unit, right? So you can actually use the number directly. However, you need to actually be able to write this, right? Okay, therefore the concentration of your Ca2 plus will equals to 9 times 10 to the negative 5. Our concentration of Cl minus will be 2 times 9 times 10 to the negative 5. Right? This is actually the only time that you actually change the concentration for your NiOn, right? Because the coefficient is now 1-to-1. Okay, then the KSP will equals to 9 times 10 to the negative 5 first power, 2 times 9 times 10 to the negative 5 second power, right? And that will be the answer. Okay, so you really need to see what is actually needed information for this type of calculation. First, correct concentration terms, right? It has to be molar solubility, cannot be the grain solubility. If it's grain solubility, convert into the molar solubility before you move on. Okay, the next step is actually make sure you know the correct concentration of your Ka and anions. Okay, then they will depending on the coefficients. Okay, once you have all those things set up properly, then just plug it in. You're on the right track. Okay, then trust yourself. Is that clear? Okay. Okay. This is actually a variance of the previous questions. Okay, so this question says that you have 1 liter of a saturated solution of CaF2 contains 0.067 gram of dissolved CaF2, whose formula weight is 78.1 grams per mole. what is the KSP of CaF2, right? Again, keyword solubility. You do not have solubility. Keyword will become KSP then. Okay, so every time we talk about KSP, the first thing that you know is actually you need to have molar solubility. Okay, read the first sentence. Do you have molar solubility? You have what? You have grain solubility, right? That is actually the time that you know you must convert that into molar solubility first, right? So that will be the first step. Second step, the species that you have is what? CaF2, right? Then you know it will be Ca2 plus 2F minus, right? So once you know the solubility of your CaF2, then you know the concentration of your calcium plus should be the solubility, right? The molar solubility for your F minus should be 2S, right? And therefore, you know your KSP will simply equals to S times 2S squared, right? So it's exactly the same thing that we just did for the previous questions. Okay, so now how do we calculate the molar solubility? So it says the molar solubility, you need to calculate the moles per liter, right? What's the volume? 1 liter, right? Therefore, you know this is 1, right? How many moles? And the way you calculate mole is what? The mass, which is 0.0167 over the formula weight, 78.1, right? Therefore, if you do like calculations, this will give you a concentration or solubility. Molar solubility equals to 2.14 times 10 to the negative 4, right? So that will be the solubility you're going to have. Okay, therefore we know the calcium 2 plus concentration will equals to 2.14 times 10 to the negative 4. But for your fluorides, it will be double of that. There will be 4.28 times 10 to the negative 4. Therefore, your KSP will equals to 2.14 times 10 to the negative 4 times 4.28 times 10 to the negative 4, the second power. And then you're going to come to a number of 3.91 times 10 to the negative 11. Yes. You mean why I put 2 here? So how do you actually write the equilibrium constant? If you have A plus B, if you C plus D, how do you define your K? How do you define like K? C to the C's power, D to the D's power, A to the A's power, B to the B's power. That's a definition, right? Okay. So in your insoluble salt, your reactant is actually solid. Therefore, you don't write any of your reactant into your equilibrium equations, right? That means you don't have this. Okay. You just write the product to its coefficient. Okay. For your CaF2, okay, once it dissociates, it becomes Ca2 plus 2F minus, right? That 2 is actually the exponent. Why do I have a 2S? Why do I have 2S here? Okay, so what is the 2S means? That's the concentration. 2S represents the concentration of the F minus, right? And they will actually relate to how much equivalent you can produce once the insoluble salt dissociate, right? So here it tells you one equivalent of CaF2 is going to produce two equivalent of F minus, right? But when we talk about solubility, is solubility of what? Your salt. Okay, so if you dissolve that much, then how much going to produce for your F minus? It will be 2 times of that. That's why I have 2s within the parentheses. Is that clear? Cool. Any other questions? All right, so this is actually how you solve this question. Okay, again, make sure you use the molar solubility. Make sure you know how to actually compute the concentration of your cation and anions. Make sure you know how to write the KSP equation. Okay, then once you do all of things right, then the answer you enter will be correct. Okay, question number 16. It says the KSP of AgCl is 1.6 times 10^10. Consider a solution that is 1.0 times 10^9 in calcium chloride, 1.0 times 10^1 in AgNO3. Okay, so then this is actually going to be a multiple choice type of questions. Okay, it's going to ask you QSP and KSP comparison. Okay, and then the answer, there's only two possible answers, right? If your Q larger than K, don't precipitate. Smaller than K, no precipitate. There's only two possibilities. Okay? So now, how many substances you have here? 3, right? One is AgCl, one is CaCl2, one is AgNO2. Okay, everybody see this, right? Which one is actually insoluble salt? Good, because it's actually the only one that have the KSP, right? Then make the other two become what? Soluble salt. Okay, that means it's going to dissociate 100%, right? Now you look at that. The first one is CaCl2, right? I mean, there's a soluble salt. The first soluble salt is CaCl2. Once they dissociate, do you see it's going to produce one of the species belongs to your insoluble salt? Yes. Which one? Cl minus. Okay, don't forget about your charge. Okay, so it's going to produce Cl minus, right? Can you see the concentration of the Cl minus from the CaCl2? It should be 2 times 1.0 times 10^9, right? Do you see why I say 2? Because it's CaCl2, right? So once one of your CaCl2 dissociate, it's going to produce 2 equivalent of Cl minus. Since your concentration of your CaCl2 is 1 times 10^9, then your Cl minus will be 2 times of that. Everybody follow the things I say? Okay. The same thing for the second species, AgNO3, right? What's the species that's relevant? Ag, what's the charge? Plus, right? NO3 is 1 minus, right? Yeah, so Ag plus. Okay, what's the concentration of Ag plus on that guy? Should be 1 times 10 to the negative 1. Okay, so you know the concentration of your Ag plus, you know the concentration of your Cl minus. Therefore, you can compute the QSP, right? And then once you get a number compared to the KSP showing up here, okay, if Q is larger than K, precipitate will form. Otherwise, there's no precipitate. It's as simple as that. Okay, so let's actually the overall large flow. Okay, but let's do the things in a more systematic way, right? Are you going to form your precipitate, right? And then the things that we know is actually if you Q larger than K, then precipitate will form. Okay, smaller than K, no precipitate, right? Let's count the underlying logic flow that you must have. Okay, so data that you have is that you have CaCl2 and concentration is 1 times 10 to the negative 9. Therefore, you know your Cl minus concentration should be twice, okay, times 1 times 10 to the negative 9. That's 2 times 10 to the negative 9. AgNO3. Concentration is 1 times 10 to the negative 1. Therefore, you know the Ag plus concentration will equals to 1 times 10 to the negative 1. Okay. Therefore, the QSP is going to become Ag plus times your CO minus. There will be 2 times 10 to the negative 9 times 1 times 10 to the negative 1. They give you 2 times 10 to the negative 10. Okay. And then your KSP is this 1.6 times 10 to the negative 10. Therefore, your QSP, which one is larger, Q or K? Q, right? So Q is going to be larger than K. Therefore, precipitate will form. Okay, so conceptually, it's actually very simple. All right, so this is actually how you do this, right? And the question, the structure of the question is always that you have an insoluble salt with certain KSP, right? And then you're going to have 2 soluble salts with certain concentration. Okay, and then for those soluble salts, okay, you want to actually identify what is actually relevant Ka-ions and Ni-ions. Okay, so you know the effective concentration of Ka-ion and Ni-ion, so that you can compute correct QSP. Okay, so this type of question, the things that students always make mistake, is always here. This, right? This is actually things they consider as a conceptual error if you don't put 2 over there. Okay, this is actually not calculation error. This is a conceptual error because you don't know that for the soluble salt, once it dissociates, one soluble salt is going to produce 2 equivalent of the anion. Okay, so that's the things that students always miss. Once you miss that, then you're going to miss the whole problem. Because you can see that the question is actually carefully designed. If you don't multiply by 2, the number you get will be 1 times 10 to the negative 10, which will be smaller than your KSP. Okay, so this is the most important part that students may actually miss. Okay, but once you understand these things, it should be actually very, very simple. Okay, I don't want you to actually lose a point like that. Okay, so this is actually what you should know for this specific type of questions. Okay, 17. What is the solubility of CaF2, whose KSP is 4 times 10 to the negative 12 in 0.35 m NaF? Okay, so again, the keyword is solubility, right? Who is actually your insoluble salt? CaF2, right? What's the other guy? The NaF is the soluble salt, right? And that guy will actually produce what common ions? What's the common ions that you're going to have for your insoluble salt? F minus, right? So the common ion is actually F minus, right? So that guy is going to produce actually a high concentration of F minus, which has a concentration of 0.035 m, right? Because the ratio is actually 1 to 1. Okay, so that's all you need to know. Okay, so how do you actually solve this? The Q is actually to find out the solubility, right? The data is actually you have CaF2. They're going to get Ca2 plus 2F minus. Your KSP is going to equals to Ca2 plus concentration times F minus concentration to the second power, right? Those are the things that you know, okay? And then if the solubility is actually S, then you know the Ca2 plus, if you don't add in any soluble salts, right? This will be S. The second term will be 2S to the second power, right? So that's actually the setup that you have. Okay. However, because today you add in this guy, right? This is the soluble salt. Okay, so NaF is going to become Na plus F minus. The ratio is actually 1:1, right? Therefore, the F minus concentration coming from your soluble salt will equals to 0.035 m. Okay, and that will go into this term, right? Therefore, this becomes S times 2S plus 0.035 second power. Everybody follow this? Everybody understand why I write in this way? Okay, so once you understand this, the next thing is actually small x approximation, right? So this is going to S times 0.035 square. It's going to equal to your KSP, which is a value of 4 times 10 to the negative 12. Therefore, the solubility will equals to 4 times 10 to the negative 12 divided by 0.035 squared. And then you are going to get a value of 3.3 times 10 to the negative 9. That will be the solubility of lead insoluble salt. Okay. So this again, we can't do these things in the chapter question. Okay, we just redo it again here. Okay. All right. So this is actually for question 17. Gosh, I have 2 more. Okay, so this is actually exactly the same questions. Okay, the KSP of Ag2SO4 is 1.2 times 10^5. What's the solubility of Ag2SO4 in 0.25 m AgNO3? Okay, again, who is actually your insoluble salt? This guy, right? And then that is actually the soluble salt that's going to produce apparently Ag plus equals to 0.25. Okay, so Ag2SO4 is going to become 2Ag plus SO4 2 minus KSP equals to 1.2 times 10 to the negative 5. Okay, therefore, this guy, the solubility will be 2S, right? This guy will be S. Okay, and then because your soluble salt is going to bring in that much of Ag plus, therefore finally you have 2S plus 0.25 for your Ag plus. This guy will be just S, right? So your KSP will equals to 2S plus 0.25 square times your S. That's equals to 1.2 times 10 to the negative 5. And then use small x approximation, right? So this becomes 0.25 squared times S that equals to 1.2 times 10 to the negative 5. Therefore, your S is equals to 1.2 times 10 to the negative 5 divided by 0.25 squared. And then you're going to get a value of 1.92 times 10 to the negative 4. Okay. So this is actually exactly the same as the previous questions. Okay, so I put 2 here just want to actually to reinforce all this logic flow. Okay, so you can interpret it itself twice. Okay. The very last questions. Okay. So it asks you, for which salt in each of the following group will the solubility depending on pH? Okay. So to solve this type of questions, you're actually looking for the anions. Okay. If it is your strong base or weak base, they'll be influenced by the pH. Okay, so first one, anion is F minus and then Cl minus, right? So F minus is a weak base, right? Because its partner is HF. HF is a weak acid. Its conjugate partner will be a weak base, right? So weak base. How about Cl minus? Neutral, because its partner is HCl, a strong acid. Therefore, Cl minus is actually neutral. Therefore, you know, among the two, this will pH dependent. Okay. Number two, BaNO32. I hope you see that's NO3 minus. The other one is actually NO2 minus. Okay. NO3 minus is neutral, right? Because its partner is HNO3, a strong acid. Therefore, this guy is neutral. Okay, and this guy will be weak base. Therefore, this guy will be pH dependent. Okay. Number three, CaOH2, anion will be OH minus. CaCO2, anion will be Cl minus, right? OH minus is a strong base, right? This one is neutral. Therefore, OH minus is pH dependent. Very last one, FeNO32, that's NO3 minus, and then Cm minus. This guy is neutral. This guy is weak base. Therefore, this guy will be pH dependent. Okay, so this very last question is actually really test you can actually recognize the anion is strong base, weak base, or neutral, right? If it's neutral, then it's not going to become pH dependent. But as long as it's actually a strong base or weak base, then it will be pH dependent. Okay, so let's say for today, yeah, I hope these things, everybody can understand the things that we talk about today. Okay.